Okay, class, so we're going to be wrapping up Chapter 8 um, with this screencast. And the material you're responsible for are sections 8.1 to 8.7. Okay, now you should read 8.8, but I'm not going to put it on the test. The next few minutes, what I'm going to do is just do a quick, brief overview of where we were at and summarize some of the equations. If you remember, we're looking at the two-body problem with central forces, and so what we're trying to do is get everything into terms of a nice, simple, one-dimensional equation, and we had basically gotten to the point where we have the Lagrangian, right, is equal to 1/2 mu, where mu is that reduced mass times r dot squared minus this potential energy, which again we're taking as central force. Now, what we had done in the last lectures, we talked about how because of this central forces, we have this conservation of angular momentum, which means the motion occurs in a plane. That means we can write this in polar coordinates, which then gives us that we have the Lagrangian can be written like this: 1/2 mu r dot squared plus r squared phi dot squared minus this potential energy, which we're not specifying for now. Okay, and then what we could do is look at the equations of motions, right? Just doing our standard technique, and we did this for both the with respect to r and then with respect to phi. And when we did this, we basically ended up with these two equations. If you'll recall that the reduced mass times r double dot is equal to mu r phi dot squared minus du dr, and then the other one we had is the reduced mass times r squared phi dot equal to L, right? So these are the two equations that we got. This came from the r equation, and then this one comes from the phi equation, and it specifies conservation of angular momentum. And then what we did to simplify this further is we basically took this, solve for phi dot here, and plug it in over here, if you remember that, okay? And when we did that, of course, we end up with an equation that looked like mu r double dot is equal to this L squared. We're getting, that's the magnitude of angular momentum. And remember, that's a constant. So then we get, again, we have this equation where we have this mu r double dot equal to L squared over mu r cubed minus du dr. But then what we decided to do is take this centripetal term and put it in as sort of an effective potential, right? That was the next thing that we did. And so we have, the net result was we ended up with this mu r double dot is equal to minus du effective over dr, where the effective potential energy term that we have looks like this: u effective is equal to u of r, our central force potential, plus this effective term associated with the centripetal motion, right? And this is what makes orbit stable, to mu r squared. Okay, so that's sort of where we were. We had talked about this in a little bit more detail, where we had basically written out what the different terms look like on that u effective, right? So we had this, again, the effective potential energy has this term of the central force plus this L squared over 2 mu r squared. And of course, u of r, the one that we're often interested in, goes something like minus 1 over r, for example, for gravity. And so we had this, or we can break this into pieces, where if we look at, this is a function of r, and this would be, let's say that L squared over 2 mu r squared, it goes something like this, right? course, for the other one, for the central potential, we have something that looks like this. Goes as minus 1 over r. It comes down like that. That's all well and good, but then when we put these together, of course, we end up with a combination of these where essentially we just have something that looks like this. Where it essentially comes down. Up like this. That's the combination of those, right? And you could imagine the different scenarios that we had briefly talked about, where if you had the total energy of the system, right? If you have the total energy is something like this, right? Then you have a situation where you're never going to have a bounded orbit, and then you could imagine that you had an energy that was somewhat less, but not at the minimum, where you might have a total energy that looks like this. And you'd see that you now have a bounded orbit, and you would have, as the motion went on in this problem, you would have something where you have an R min and an R max, and that's going to be something that gives you elliptical motion. We'll go into more detail on that in just a minute, but this is just kind of a qualitative understanding. Of course, if you had that E total look like that, right, then you basically would have a circular orbit. But again, the important thing is that this term basically gives you that stability at some range of r, in a situation like this, right? So you end up with a bounded orbit where you don't have things taking off or crashing into, the two particles crashing into each other for a certain energy range, okay? And that starts to give you some qualitative feel for what's going on. Now what I want to do is just, look at this in a little bit more detail and just remind you that you do have this situation of what the energy is in this system, okay? So just go look at this real quickly. Again, this is still kind of just review, so I'm going to go through it fast. You have this mu r double dot is equal to minus the gradient of this effective one-dimensional potential. Right, now what I'm going to do is I'm going to multiply through by r dot. Okay, and when you do that, you get this. You get mu r dot r double dot is equal to minus r dot du effective dr. This term here basically just becomes minus dr dt, right? Du effective dr. The dr's cancel, and so you can write this one out as minus du effective dt. And then of course this one over here, this one is just basically equal to d dt of 1/2 mu r dot squared. Okay, so then that's equal to this minus du effective dt, and then we can write this in the following way: d dt of 1/2 mu r dot squared plus u effective is equal to 0. Now, if you look at that expression inside of the derivative, this term here, that's just the energy, and so the time rate of change of the energy is equal to 0, that means we know it's equal to a constant, right? And so we can basically just then say that you have 1/2 reduced mass r dot squared, and then you have the second term, which comes from the centripetal motion, plus 1/2 mu r squared phi dot squared, right, plus u of r is equal to some constant we can just call E total if you want, okay? And so that really shows you that we've cast this equation, or this problem, this two-body problem, into a one-dimensional problem, right? And then we can start writing things out like what I did on the previous page, where you kind of have this total energy that I put here is equal to this, you know, and you can then again start to see these, but you have these energy that looks like this, potential energy looks like this, and you can have these bounded orbits, okay? Now, of course, it is important to kind of keep in mind that you don't want to totally forget the phi motion, right? Right, because you have that phi dot is equal to this L over mu r squared. That's just the conservation of angular momentum. And then, of course, you also have the v phi is equal to r phi dot. And, of course, you see that this increases as r decreases, right? And this also increases as r decreases. Right. Again, you know, the way to look at this is just conservation of angular momentum, just like the ice skater. You know, if you're changing r, if you're making r smaller, then to keep the angular momentum constant, phi dot has to increase, right? So it's just kind of important to keep those things in mind, okay? And then we had talked about, you know, a little bit about how you could imagine a problem like this. Again, this is just still qualitative, but you could imagine, you know, that you have something like this, and we'll go into more details in this, on this just a second, where you might have something like the sun. You know, and then we talked about the case of maybe you have Mercury, right? And then you have some sort of elliptical orbit that might, you know, I'm just exaggerating it, but it might look something like this, right? And this minimum distance is called the perihelion. R min, and then this longest distance of the ellipse, I call that the aphelion. Right, and that would be R max. Again, that's this distance here, just to be clear. Okay, and again, the perihelion is this shorter one here, right? And then we had talked about, which I thought is pretty neat, that the perihelion of Mercury precesses, and we said it precesses about 574 arc seconds per century. Remember, there's 3,600 arc seconds. Let's write like that. Is equal to 1 degree. Right, so this is a very small amount, but there's perturbation. This, what we'll see in a second, is if you really had this isolated two-body system, there would be no precession of this perihelion. It would be constant. In other words, as you made one full orbit like this, the perihelion would be in the same place, but perturbations from the planets can cause this to precess. In other words, each full revolution it has slightly shifted an angle, right? And even quite some time ago, the perturbations from the other planets were known to be to give a large fraction of this. So the perturbation from the other planets was about 531.6 arc seconds per century. Okay, but that left this discrepancy of about 43 arc seconds per century, right? And this was accounted for by Einstein using general relativity, which was really one of the big successes, where he did the calculation, and when he did the calculation, he basically got 43 arc seconds per century, which when added to this perturbation from the other planets basically gave the total expected precession of the perihelion of Mercury. So that was kind of a big deal. Okay, so now what we want to do is look at this, study the orbit of this two-body problem in a little bit more detail. And now if you were just to take this equation that we have, this mu r double dot is equal to minus the gradient of this effective potential with respect to r, right, which is equal to, again, minus du dr, where that's our central potential, plus this centripetal effective potential term, L squared over mu r cubed, you see that this would be maybe a little bit of a tricky differential equation to solve. So what we're going to do is do some kind of nice, I guess, mathematical tricks to simplify this equation. So bear with me for a few minutes while we do this, and then you'll see that that allows you to really get a very clever solution to understand the orbits in this two-body problem for a central force. Okay, so that's what we're going to do in the following. All right, so let me just get this equation pasted here. So this is our equation that we're starting with. Let me just make it a little smaller so I have some room. Okay, so that's the equation that we're starting with, and what we want to do is do some work on this, and I'll call this equation A, okay? This is just our well-known equation. Now, I'm going to do a couple of substitutions. The book uses little u, but as you can see, I have big U, I have little mu, and my writing's hard to distinguish things, so what I'm going to do is I'm going to use G, okay? Now, here's the things that we're going to do, and call them what you want, but I'm going to call it trick number 1, okay? And the trick number 1 is basically we're going to make substitution. R is equal to 1 over G, or if you like, G is equal to 1 over R, okay? Trick 2. This one's a little bit more complicated. We're going to replace the derivatives with respect to time in R double dot, for example, with this d phi dt, which is just phi dot, remember, d phi. I wrote it like this just so you can see that the d phi's cancel out, and that is in fact equal to a ddt, but that's equal to phi dot derivative with respect to phi. But remember, phi dot is just equal to L over mu r squared d phi, or it can be written like this, L g squared over the reduced mass times d phi. Okay, so those are our little tricks. Now, we're going to use these. Use these two things here to basically rewrite A. Okay, that's really our goal. Okay, so therefore, if we look at this, we have R dot can be written as LG squared over mu times d phi of 1 over g, right? Because that's just equal to R, and that's equal to LG squared over mu times minus 1 over g squared dg d phi. Things cancel out, and then this becomes equal to minus L over u, because the g squared's canceled out, right? dg d phi. Okay, fine. But now we just have to do the same thing again and to get r double dot. So r double dot is now equal to L g squared over the reduced mass times this whole thing again, d phi of what we already had for r dot, right? And that's just this minus L over mu times dg d phi. That's equal to minus L squared g squared over mu squared times d squared g d phi squared. Okay, now we plug this. Okay, that's what we do. And so then we end up having that the reduced mass times r double dot is equal to, one of the mu's cancels out, so this gives me minus L squared g squared over mu times, I'm going to do this like this now, g two primes, right? I'm not going to use the dots because we use those for our time derivatives, but that's the second derivative. Those dashes are derivatives with respect to phi, and we know that that's equal to basically our central force, right? Because minus du dr is just equal to our central force. I'm going to put it as central. I think the book just uses F, but I'll put it as C for central, plus L squared G cubed times mu. Okay, so you're wondering if this is getting anywhere. Now what I'm going to do is just multiply through I minus mu over L squared G squared. Okay, and when I do that, well, I get this pretty neat equation. Look at this. This is what I get. This side just becomes G, second derivative of G with respect to phi, and that's equal to minus G of phi, right? That comes from this term. The only thing left is a G, and then you have then minus the reduced mass times L squared times G squared of phi. I'm just putting in the phi there just to remind us that the G does depend on phi, times F, our central force. Okay, where again, remember, G is equal to 1 over R. Okay, and I'm telling you that this is a nice equation that we're going to look at, and you'll see how the substitutions make this how these substitutions are really useful in terms of gaining some insight into this problem, and we'll see that in just a second. But the point being, this is a nice equation, and it'll show on the following page. Okay, so let's go ahead and do that. Let me paste that equation here again. Give me 1 second. Paste. So we have this as our equation, okay? And I would note that this holds for any central force, okay? Because we haven't specified that central force yet. But now let's look at this in terms of the Kepler orbits, okay? Which really just means we're going to take the central force, F central, is equal to what we know for gravity, minus G m1 m2 over r squared. We're just going to say that's equal to minus this gamma over r squared, where gamma we know is just equal to G times m1 times m2. Okay, so that's what we're working on. So now we basically plug in for the central force, and this is kind of the interesting step, okay? So now we're going to plug this in. Okay, and so when we do that, we end up with G double prime. I'm going to just drop the phi subscripts now, since we know this is dependent on phi, and then is equal to minus G, right? Then we have this minus mu over LG squared times minus gamma times G squared. Because remember, recall, G is equal to 1 over R, so this is equal to minus gamma G squared, right? But this is where the really cool thing happens. If you look right here, this cancels this, and this suddenly starts looking like something we can handle, right? And I'll explain that more in just a second, but you should already be starting to see this. This is minus G, right? Plus mu gamma over L squared. Looks like I lost a square there, but I just added it back in. So again, now our equation looks like this, just to be complete. This is G double prime of phi is equal to minus G of phi plus mu, reduced mass, gamma, this over L squared. L squared is the magnitude of the angular momentum, right? That's just a constant. This is just a constant, right? Now if you look at this part, well, that certainly looks like it's just our harmonic oscillator, right? A second derivative with respect to phi, and then we have a restoring force. This is a nice little minus sign, and so we see that this starts to look like something that we can investigate, okay? And so that's what we're going to do, but let me just make sure we're clear on something. I'm actually going to write this down, so just so you're clear where we're at, right? The reduced mass, if you recall, is equal to m1 m2 over m1 plus m2, right? Again, that shows up in this equation. We have that gamma is equal to gravitational constant times m1 times m2. That's just a constant. And then, of course, we have that L is equal to the magnitude of angular momentum, which we know is a constant. Okay, so now what we want to do is look at this equation in a little bit more detail. We're just going to do a simple substitution. Okay, we'll do that on the next page. So what I'm going to say is the following. Well, let me just write this down so we have it. G double dot is equal to minus G plus mu gamma over L squared. Okay, make sure that's right. So what I'm going to do is the following. I'm going to let W equal G minus mu gamma over L squared. Now if I take the second derivative of that, it's kind of clear that I'm going to end up with W, second derivative of W with respect to phi is equal to the second derivative of G with respect to phi, just because this term here is a constant. Okay, well then when I compare this and this, I see that I can basically write down the following. I have that W double prime is equal to minus W. But we know the solution to that, right? Because this is just a simple one-dimensional oscillating system, right? So that's kind of the point. You see all this work we did for this two-body problem to get it in terms of a one-dimensional problem has allowed us to get this nice solution. And so we know just by inspection at this point that W is equal to the amplitude times some, say, cosine of phi minus phi naught, right? You know, for the purposes here, we can basically ignore phi naught by setting equal to 0 in appropriate direction. And that's just, you know, that's just saying something about the initial condition, okay? But now what does this tell you? Look at this. Now we have that G is equal to W plus mu gamma over L squared. All I did was look at this and bring this term over to the other side, right? But we already know the solution to W, right? So this is then equal to gamma mu over L squared plus A cosine of phi. Right? I'm going to pull out a gamma mu over L squared. That's going to give me a 1 plus A L squared over gamma mu times cosine phi. Okay. Now I'm going to just do some simple things here. I'm going to basically write this as 1 over C times 1 plus epsilon cosine phi, where basically I let epsilon, and these will have some meaning in a couple of minutes, A L squared over gamma mu, and C is equal to L squared over gamma mu. Okay, so we've simplified this and we have some sort of solution to this problem that we can now look at in more detail. Okay, so let's now look at this. Okay, start to think about this. Again, we now have G, which is equal to 1 over R, if you recall, is equal to 1 over C times this 1 plus epsilon cosine of phi. But what's neat is we can now rewrite this, right, as R of phi is equal to C over 1 plus epsilon cosine phi, right? So that's a pretty nice result that we're going to spend a little bit of time looking at. Where again, let's remind ourselves that C is equal to L squared, the square of the magnitude of the angular momentum, times this gamma, which is G m1 m2, times the reduced mass mu, epsilon is equal to a L squared over gamma mu. Now these will be related to the properties of the ellipse, as we'll see in just a minute. Right, so it's kind of interesting that these terms here determine which makes sense, the details of this ellipse. And we'll look at that in just a second. A couple things you should look at. Convince yourself. One, you should verify the following: that epsilon is unitless, as it has to be, right, just by looking at this. And of course, therefore, that means that C has units of length. Okay, but you can verify those for yourself. Okay, so now what we're going to do is we're going to consider the case of a bounded orbit. Okay, so bounded. R should be finite. Okay, therefore should have epsilon less than 1, because then the denominator and the denominator is finite and positive. Okay, so let's look at this. Let me just put this. The maximum you could have, of course, is when phi is equal to pi. So R max is equal to C over 1 minus epsilon. Right, that's when phi is equal to pi. Right, and this is what we call this occurs at the aphelion as we defined it earlier. Okay, and then we have R min is equal to C over 1 plus epsilon. Okay, and that occurs for phi is equal to 0, and that's for the perihelion. Okay, so that puts us in a pretty good situation, but you know, this does give us an equation for an ellipse. Okay, this does, but that's not obvious. So what I'm going to do next is essentially show how that happens, which is essentially going to be problem 8.16 from the book, and we'll go into the details of that next. Okay, so now we want to look at this in a little bit more detail, and we're looking at the case for the bounded orbits. Okay, and so again, we want to write this in the form that we see that this equation that we have is in the form of an ellipse, and we're taking the case where epsilon is less than 1. So essentially what I'm doing, I'm going to write this out in terms of the parameters of an ellipse, then we'll go through the math to see that it works out. Okay, so again, let's just start with where we're at. We have this R phi is equal to C over 1 plus epsilon cosine pi, right? That's where we're at. Where again, remember we have C is equal to L squared over gamma mu, and we have that epsilon is equal to A L squared over gamma mu, and we know what each of these terms is. Just remind you that that capital A is the amplitude from when we solve the differential equation, which comes from the initial conditions. Okay, so now what we want to do is basically cast this into the following form. An ellipse in Cartesian coordinates, where we have x plus d squared, so we're going to be offset from the origin along x over a squared plus y squared over b squared is equal to 1. And I think that we all recognize that as the equation for ellipse. And now in terms of these parameters that we have from solving our problem, we're going to see that a is equal to C over 1 minus epsilon squared. B is equal to C over square root of 1 minus epsilon squared. And D is equal to A times epsilon. Okay, where we're going to have epsilon is called the eccentricity. Okay, and B over A is equal to square root 1 minus epsilon squared. This is the ratio of major to minor axis. Okay, and then this D is basically distance from, let's say, object to, we could say, maybe think of it as the sun, and the Earth's going about the sun, to center of ellipse. Okay, so let me just draw all this out in a pictorial fashion. This might take a second, so just give me a minute. We'll draw it nice and big and try to get everything labeled and talk about it, and then we'll show, after we do that, then we'll show that this can be written in this form. Okay, but first let's just draw everything out graphically so we can kind of see what's going on. So I'm going to draw an ellipse. Okay, so here's the ellipse. Might take a couple times to get this right, but let me just try, see what we can get. Let me get the black pen. Let me try that again. Let's see. Okay, that looks pretty good, so we can work with that. All right, so I'm going to draw the center of the ellipse, which is about right here. This is the center, roughly. I'm just eyeballing it. That's the center. And then we have the semi-major and semi-minor axes, which we'll label as, call this one B, call this one A. Again, this is the center of the ellipse. And now the way I'm going to draw this is, object 2 that I mentioned, which could maybe be the sun, might be at one of the foci of the ellipse, so that could be here. Let's just call this, we're going to call that the O for the origin, and then this distance here is D. Okay. Then we have this distance here at 90 degrees. This is C. And then we're going to call this direction X. I'm going to call this direction Y. And then, of course, we have the angle defined from here. This is our phi. Of course, this would be where, let's say, M2 is, and this would be, for example, where M1 is. All right, so we kind of have everything labeled. And we have, of course, just to be complete here, this distance here. This is our R max. This is our aphelion. And then this distance here is R min. think that has everything defined in it. And yeah, that has everything that we wanted to find in it. Let me just point out here that you see that this distance here at 90 degrees is equal to c, and you can see that just from looking at this. When this is 90 degrees, this becomes 0, and so at phi equal 90 degrees, this distance is just c. So that's where you can see that. Okay, so that kind of shows you what we're looking at. Now let me also draw, just as a reminder, it's nice to kind of connect this up with that energy picture we had, right? Here's R, and I'm plotting that mu effective. Oops, not mu, U effective. Remember, it kind of goes something like this. Down with minus 1 over R. Oops, let me draw this a little nicer. Well, actually, it comes down with R squared. I'll get it right eventually. It comes down with R squared, something like that, and then comes back up. It goes like this, right? And remember, we could have some energy, E total, which is a constant. For a bounded orbit, it has to be below this. What I have marked as 0. So, maybe it's here. Maybe something like this. E total, right? And then we would have these distances here. This would correspond to R max. And this would correspond to R min. Okay. So now the next step we want to do, as I said, is to really just show that this can be written in this term. Okay, so I'm gonna kind of sketch this out on the next page. Okay, it's fairly straightforward. It's just some algebra, but I just want to sketch it out so that you can come back and convince yourself that what we have here, for all this notation, makes sense. Okay, and that really, think about this. We got this from this rigorous solution from the Lagrangian for a two-body problem, and it does specify all the details of this elliptical orbit, where again we're dealing the case with the bound orbit where we have epsilon less than 1. Okay, so now let's just look at this and finish up talking about this bounded orbit. And so this is to show, again, we basically want to show that R equal to this C over 1 plus epsilon cosine phi can be written in the form of an ellipse. And this is basically, also just so you know, it's not a homework problem that was assigned, but it is a problem from the book 8.16 from Taylor. Okay, so we have basically now R plus epsilon R cosine phi is equal to C. I just multiplied through. Okay, but we know that R cosine phi from polar coordinates is just equal to R, is equal to X, right? So this gives me R plus epsilon X is equal to C, or R is equal to C minus epsilon X. Okay, so now if I square this, I basically end up getting, so I'm going to square this. Okay, when I do that, I end up getting R squared is equal to C squared minus 2C epsilon X plus epsilon squared X squared, right? Which then gives me, remember, R squared is equal to X squared plus Y squared. So that's equal to C squared minus 2C epsilon X plus epsilon squared X squared. I can bring over some terms to the other side, and so now I have, just bringing things over, I have 1 minus epsilon squared times x squared plus, I just brought this whole other term over, plus 2c epsilon x, right, plus y squared is equal to c squared. Okay. So now I'm just going to divide. I'm going to divide 2 by 1 minus epsilon squared. So that will give me x squared plus 2c epsilon 1 minus epsilon squared x plus y squared over 1 minus epsilon squared is equal to c squared over 1 minus epsilon squared. I'm going to define v as being c epsilon 1 minus epsilon squared. That's just going to come in over on this term over here now. And when I do that, I end up with x squared plus 2dx plus y squared over 1 minus epsilon squared is equal to c squared over 1 minus epsilon squared. Okay, so now what I'm going to do after that is add d squared to both sides. 8 square on left side. Okay. When I do that, I basically end up with the following. We're starting to make some progress. We got x plus d squared plus y squared over 1 minus epsilon squared. That's equal to c squared over 1 minus epsilon squared plus c squared epsilon squared over 1 minus epsilon squared, right? That's just d squared written out. And what you'll find out is you can collapse this right-hand side, will simplify to c squared over 1 minus epsilon squared, okay? And I'm going to call that a, right? C squared over 1 minus epsilon squared. But now when I do that and divide 2 by a squared, I end up having x plus d squared over a squared plus y squared over a squared times 1 minus epsilon squared, right? And that's equal to 1. But then we just basically define b, well, yeah, b is equal to a times square root of 1 minus epsilon squared. Okay, and so that gives us our answer, right? We now have basically shown that this, right, this one here, can be written in terms of an ellipse as shown over here. Okay, and then what you need to do is go back and look at that and think about it in terms of what I've drawn here. Oops, what I've drawn here in terms of properties of this ellipse. Okay, so now we're almost done. I just wanted to do one more thing where, recall what we were doing just now, we were talking about bounded orbits. Okay, so bounded orbits was for epsilon less than 1. Now you can have unbounded orbits where you have basically epsilon greater than or equal to 1. Okay, that's a non-bounded orbit. Okay, and I'm just going to look at the specific case of epsilon equal to 1, which then gives the following. Gives us that we have basically from this equation here, R equal to C over 1 plus epsilon cosine phi. We just got this is equal to 1 plus cosine phi. Right? So we're just going to look at that. And basically what you see is that this equation, let me just get right here, R is equal to C over 1 plus cosine phi. This basically implies R goes to infinity at plus or minus pi. So you could pretty much say that that's an unbounded orbit, right? You kind of basically R goes to infinity. The object M1 is moving away from object M2. Okay, so then now we can write this out, and so what we would have is multiplying through, we have R plus R cosine phi is equal to C, or we're doing the same thing as we did on the previous page now. It's a little simpler in this case. R is equal to C minus X. So let's square that. Right, and then you're going to basically get that you have x squared plus y squared, that's just the r squared term, right, is equal to c squared minus 2cx plus x squared. You can then simplify this and say that we basically have the x squared cancel out, right? So we have y squared is now equal to c squared minus 2cx. And this gives that 2cx is equal to c squared minus y squared. Okay? And then you basically end up getting that x is equal to c over 2, just divided through by 2c, minus y squared over 2c. This is a parabola. Okay, so it looks something like this. Just sketch it over here real quick. Here's x, here's y. You know, again, it's displaced. Here's basically the center, and then you have a parabola that goes off like this. And then this distance here is c over 2. Okay, and we know that r min, this distance of closest approach, r min, is when y equals 0. Okay, and this is equal to c over 2. But we've defined c, as you can see, this is equal to L squared over 2 gamma mu. Right, and you could simplify that. I mean, you could plug in for the other things if you wanted, and I think this ends up giving L squared over 2 G M. You can put this as mu squared like this. Okay, so fine. That's the case. That's a case for the unbounded orbit when epsilon is equal to 1. You get this parabola. Okay, and I'll just say it. I'm not going to go through it, but for epsilon greater than 1, you then get the orbit. The motion becomes in hyperbola. Okay, and that's discussed a little bit more in the book, and you can look through it. But I think this is all that I want to say for Chapter 8. So on the next lectures, when we'll be back in class, we're going to start up on Chapter 11. Okay, that's the last chapter that we'll cover in this class. See you on Monday.